300 feet beneath the Hoosac Mountain, there is no day, no wind, no weather, only the mathematical certainty of stone and the smell of burned kerosene hanging in the motionless air. The tunnel face glows amber under a dozen oil lamps. The drillers work in pairs, one man holding the iron bit steady, the other swinging the 8-pound hammer. 8 hours of this. 16 inches per shift if the rock cooperates, 6 inches if it doesn't. But they're not the ones the engineers watch. The engineers watch the man with the canvas satchel. He kneels at the tunnel face. His hands move with surgical precision. He measures the depth of each borehole with a wooden dowel. 12 inches, 14, 9.5. He calculates the charge weights in his head, ounces converted to grams, adjusted for rock density, corrected for moisture content. This is the powder monkey. Not a child, not anymore. By 1870, that word means something different. It means the human algorithm, the man whose mental arithmetic determines whether the mountain moves forward 8 feet or collapses inward on 30 workers. He opens the satchel. Inside, 22 tin cartridges, each containing exactly 3 ounces of blasting gelatin, a nitroglycerin compound so unstable it can detonate from a 3-foot drop onto granite. He begins to load. 1 cartridge per hole, tamped with clay, sealed with a wooden plug. Each movement identical to the last, no variation, no improvisation. Muscle memory built through 1,000 repetitions, refined by the survival of those who got it right and the absence of those who didn't. The fuse comes last. He unreels 18 feet of Bickford safety fuse, tarred hemp wrapped around a powder train, burning at exactly 30 seconds per foot. The fuse is a British invention, patented in 1831 by William Bickford, a Cornish leather merchant who watched too many miners die from unreliable ignition systems. The design is elegant. 3 strands of jute twisted around a powder train, waterproofed with tar, producing a burn rate consistent enough to bet your life on. 9 minutes. That's the math. Light the fuse, walk, don't run, 300 feet through ankle-deep water and loose muck to the safety barrier. The water is constant in these tunnels, groundwater seeping through microfractures in the rock, pooling in the low spots, never draining because there's nowhere for it to go. Your boots squelch with every step. The air pressure at this depth makes your ears pop if you swallow wrong. 9 minutes if the fuse burns true. 7 minutes if there's a flaw in the weave. Instant if the vibration from his own footsteps triggers sympathetic detonation in the gelatin. He lights it. The powder monkey doesn't look back. He walks, one boot in front of the other. Lamplight recedes behind him. The fuse hisses like a living thing in the dark. This is not courage. This is industrial process. This is the job. And for 60 years, this job built the modern world. 66 pounds of explosives detonate in sequence. The mountain shudders. Dust billows 300 feet up the shaft. When it clears, 8 feet of stone has been converted to rubble. The powder monkey walks back to the face. Tomorrow, he'll do it again. But first, we need to understand why the world needed men like this at all. 1825. The Erie Canal opens. It costs $7 million and takes 8 years to build. It makes New York the richest city in America. Every other city notices. Boston wants a canal to the Great Lakes. Philadelphia wants a tunnel through the Alleghenies. Baltimore wants a railroad to the Ohio River. And all of them face the same problem: geography. By 1850, the technology exists to drill holes. The Burley steam drill can punch a 2-inch bore 18 inches deep in 30 minutes. That's revolutionary.
Before steam, that same hole took 2 men 6 hours with hand hammers. But drilling holes doesn't move rock. That requires explosives, and explosives require human judgment. This is the industrial bottleneck. Machines can automate the drilling. They cannot automate the detonation. The chemistry is too volatile. The geology is too variable. Rock doesn't break in predictable patterns. Quartz shatters. Limestone crumbles. Granite fractures along invisible planes that shift every 10 feet. You can't program that. You can only learn it. So the engineers develop a system. The drilling is mechanized. The blasting is not. Each tunnel project employs a cadre of powder monkeys, men trained in explosive chemistry, structural geology, and a very specific kind of applied mathematics that exists nowhere in textbooks. Fuse math. It works like this. You have a tunnel 500 feet deep. You've drilled 40 boreholes arranged in a specific pattern called a burn cut. 8 holes at the center, 32 around the perimeter. Each hole is 14 inches deep and angled to create maximum fracture propagation.
You need to calculate the charge weight per hole, adjusted for rock density and moisture, the fuse length required to walk the escape distance before detonation, the delay timing between center and perimeter charges to prevent sympathetic detonation, the probability of fuse failure at varying humidity levels. Get it right, you advance the tunnel 10 feet. Get it wrong, you bury everyone. This is why powder monkeys are paid more than foremen. This is why their names appear in the project ledgers alongside the chief engineers. This is why, when a tunnel fails, the first question investigators ask is, who was loading? Consider the Hoosac Tunnel. 4 3/4 miles through solid schist. Started in 1851. Projected completion, 4 years. Actual completion, 1875. 24 years, 1,000 workers, 195 deaths. The delays weren't due to lack of ambition. The Massachusetts legislature authorized $10 million before the first shovelful of dirt was moved. The delays came from physics. The mountain didn't care about legislative appropriations. The Hoosac schist is metamorphic rock formed 500 million years ago during the tectonic orogeny. It's hard, laminated, and shot through with quartz veins that turn drill bits into scrap metal. The early contractors tried hand drilling, 2 men per hole, 8 inches to punch 18 feet. At that rate, completing the tunnel would take 140 years. The Burley steam drill changed the equation. 30 minutes per hole instead of 8 hours. But that still left the fundamental problem. Drilling creates holes. Explosives create tunnels. And explosives require someone to handle them. The problem wasn't labor. The problem was that every foot of progress required a human being to walk into a hole in the ground carrying 70 pounds of high explosive and then calculate in real time how to not die. The machine age had arrived, but the machines still needed priests. And those priests needed better gods than black powder. Black powder had been blowing things up for 600 years. It was safe, stable, predictable. You could drop a barrel of it off a cliff and it would just burst open and spill. To make it explode, you needed heat and confinement. That's why it worked in firearms. That's why it worked in mining. But it was slow. Black powder doesn't detonate, it deflagrates, burns rapidly, building pressure until the container fails. In a gun barrel, that's exactly what you want. In a borehole, it's inefficient. You're not trying to push a projectile. You're trying to fracture stone. And stone doesn't care about pressure buildup. Stone cares about shock waves. That's what nitroglycerin does. 1847. Italian chemist Ascanio Sobrero synthesizes glycerol trinitrate by adding glycerin to a mixture of nitric and sulfuric acids. The result is a clear, oily liquid that is, molecularly speaking, desperate to stop existing. The chemistry is straightforward. 3 nitrate groups attached to a glycerin backbone. The molecule is saturated with oxygen and nitrogen in close proximity, a configuration that wants to become nitrogen gas, carbon dioxide, and water vapor. The activation energy required to trigger this transition is remarkably low. A sharp impact, a temperature spike, sometimes just time and humidity. When nitroglycerin detonates, the reaction propagates at 25,000 feet per second through the liquid. That's 7 times the speed of sound. The pressure wave peaks at 3 million pounds per square inch. Rock doesn't compress at that pressure, it shatters. The fracture propagates faster than the elastic wave speed of the stone itself. Granite becomes powder. Nitroglycerin is a high explosive. It doesn't burn, it detonates. The entire molecule decomposes simultaneously, releasing energy at 15,000 feet per second. That's 4 times the speed of sound. That's fast enough to shatter granite like glass. It's also unstable enough to detonate from vibration, temperature change, or sunlight on a humid afternoon. 1866. A crate of nitroglycerin explodes on the docks in San Francisco, killing 15 people and cratering the wharf. Wells Fargo bans its shipment. Railroads refuse to carry it. Insurance underwriters classify it as an act of God. And tunnel projects start buying it by the barrel. Here's why. Economics. Black powder costs 6 cents per pound and advances a tunnel face 3 feet per blast. Nitroglycerin costs 40 cents per pound and advances it 12 feet. The math is simple. 4 times the progress at 7 times the cost equals a 50% reduction in project duration. That's the difference between profit and bankruptcy. So the engineers make the calculation. They factor in the casualty rate, 1 death for every 100 pounds of nitroglycerin used. They factor in the replacement cost of a powder monkey, 2 weeks' wages to train a new one. They factor in the insurance premiums and the political optics of publicized accidents. The numbers work. By 1870, liquid nitroglycerin is standard on every major tunnel project in North America, and the men loading it learn a new liturgy. Keep the temperature between 50 and 70 degrees. Below 50, it crystallizes. Above 70, it sweats. Sweating nitro is contact sensitive. Measure by weight, not volume. 3 ounces per charge, plus or minus 2 grams. More than that and you risk overbreak. Less and you waste a hole. Tamp with clay, never sand. Sand creates friction. Friction creates heat. Heat creates... Well, you don't finish that sentence. The casualty records from this era read like actuarial tables. The Central Pacific Railroad loses 14 powder monkeys in 1868. The Hoosac Tunnel loses 9 in 1870. The Musconetcong Tunnel in New Jersey loses 6 in a single incident when a loader drops a tin cartridge from a height of 4 feet. That's the problem with liquid explosives. Margin for error, 0. The solution arrives in 1875, Alfred Nobel's blasting gelatin. Nobel's innovation wasn't discovering a new explosive, it was stabilizing an existing one. He dissolves 7 to 8% nitrocellulose in nitroglycerin, creating a gel with the consistency of thick honey. The nitrocellulose acts as a molecular scaffold, preventing the nitroglycerin molecules from moving freely. This dramatically reduces sensitivity to shock and temperature variation. The gel retains 92% of nitroglycerin's explosive power, but requires a blasting cap to detonate. You can drop it, burn it,
shoot it with a rifle. Without the sharp shock wave from a fulminate cap, it won't detonate. This transforms explosive handling from alchemy to manufacturing. The product becomes reproducible, transportable, and, critically, insurable. Nobel dissolves nitrocellulose in nitroglycerin, creating a gel with 92% of the explosive power and 10% of the sensitivity. You can drop it, burn it, shoot it with a rifle. It won't detonate without a blasting cap. This changes everything. Suddenly, you can pre-package charges, ship them in standardized tins, load them with mechanical precision. The powder monkey's job shifts from alchemist to technician. The risk doesn't disappear. Blasting gelatin is still 8 times more powerful than black powder, but the chaos becomes manageable. By 1880, gelatin dynamite is standard on every major excavation project worldwide. The casualty rate drops by 70%. Tunnel completion times drop by 40%. The modern world speeds up. But the job itself, the walking, the loading, the lighting, the running, that doesn't change, because blasting gelatin still requires a fuse, and a fuse still requires someone to light it. The powder monkey reports to the magazine, a reinforced shed built 200 yards from the tunnel entrance. Inside, 800 pounds of blasting gelatin stored in tin-lined crates packed with sawdust. The temperature is regulated by ice blocks in summer, charcoal braziers in winter. Too hot or too cold, and the gelatin becomes unpredictable. He signs the logbook, takes custody of his daily allotment, 24 cartridges, 6 pounds total, plus 200 feet of Bickford fuse and a tin of copper blasting caps. Then he walks to the tunnel. The descent takes 10 minutes. Wooden scaffolding, iron ladders. The temperature drops 2 degrees for every 100 feet. By the time he reaches the working face, it's 53 degrees, and the air tastes like wet stone and lamp oil. The drillers have been working since 5 a.m. They've punched 36 holes in a pattern predetermined by the shift engineer. 8 center holes drilled at a 10-degree convergent angle, forming a V-shaped cavity. 28 perimeter holes angled outward at 5 degrees. This is the burn cut. The center charges fire first, creating a void. The perimeter charges fire second, fracturing toward the void. If the timing is right, you get clean breakage and minimal overbreak. If it's wrong, you get a pocket collapse or worse, a hang-up where half the charges detonate and the other half remain armed and buried in loose rock. The powder monkey inspects each hole with a wooden dowel. Depth, diameter, angle. Some holes are wet, groundwater seepage. Some are fractured, the drill bit wandered. These require adjusted charges. Wet holes get an extra 10% gelatin to compensate for thermal loss. Fractured holes get 20% less to prevent overpressure. He does the math in his head. No slide rule, no tables, just memorized conversion factors and a decade of pattern recognition. The loading begins.
1 cartridge per hole. Inserted gently, no forcing. If the fit is tight, you enlarge the hole with a wooden reamer, never metal. Metal sparks. Sparks detonate gelatin. The blasting cap goes in next, a copper tube the size of a cigarette filled with fulminate of mercury, an initiator explosive that detonates from flame. The cap is crimped onto the fuse with a hand tool. Too loose and it falls off. Too tight and it detonates in your hand. Mercury fulminate is a primary explosive. It detonates from heat, impact, or friction. The chemical formula is HgCnO2. It's synthesized by dissolving mercury in nitric acid, then adding ethanol. The resulting crystals are white, unstable, and sensitive enough that static electricity can set them off. Packed into a copper tube with just enough material to create a shock wave, typically 40 grains, about 2.5 grams, it becomes a reliable initiator. The crimping tool is specific, a hand-operated press with calibrated jaws that compress the copper tube around the fuse without creating a sharp bend. Sharp bends create stress points.
Stress points fail under pressure. A failed crimp means the cap separates during the blast, the fuse burns out, and you have an armed, buried charge with no visible indicator. Then the fuse is threaded through the hole and secured with a wooden plug. The plug is tamped with clay, damp, not wet, to seal the hole and maximize explosive pressure. 36 holes, 90 minutes of work, every movement identical, no variation, no shortcuts, because shortcuts kill people. Now comes the fuse math. Bickford fuse burns at 30 seconds per foot under standard conditions, 65% humidity, 55 degrees Fahrenheit, sea level atmospheric pressure. Deviate from those conditions and the burn rate changes. High humidity slows it, low pressure speeds it. Temperature shifts create exponential variation. The powdermonkey measures the ambient conditions with a pocket thermometer and a wet bulb hygrometer. He consults a mental lookup table, not written anywhere, just stored in memory through repetition, and adjusts the fuse length accordingly. Today's calculation, 72% humidity, 53 degrees. Add 12% to the standard burn time. That's 34 seconds per foot instead of 30. The tunnel is 420 feet from face to safety barrier. Walking speed, 3 feet per second. That's 140 seconds. 2 minutes, 20 seconds to reach safety. Add a safety margin. Double it. 4 minutes, 40 seconds. Convert to fuse length. 4 minutes, 40 seconds at 34 seconds per foot equals 8 feet, 2 inches. He cuts the fuse, measures it twice, attaches it to the charge cluster. Then he lights it.
The fuse sparks white in the lamplight. He watches it for 3 seconds, long enough to confirm stable ignition, short enough to maintain his timing window. Then he turns and walks. Not runs, walks. Running increases heart rate. Heart rate increases error probability. Error probability increases fatality risk. The actuarial tables prove it. Workers who run have a 38% higher accident rate than workers who walk. So he walks, one boot in front of the other. The tunnel walls slide past in amber lamplight. Behind him, the fuse hisses its countdown. Ahead, the safety barrier. 6 feet of packed earth and timber waits at the 300-foot mark. He reaches it with 90 seconds to spare. The other workers are already there. 16 men pressed against the barrier, hands over ears, mouths open to equalize pressure. They wait. The blast wave hits the barrier like a physical thing. Dust roils. The lamps flicker. The air pressure spikes, then drops. Ears pop. Then silence again. The powdermonkey waits 10 minutes for the dust to settle and the fumes to dissipate. Then he walks back to the face. 7 feet of stone have been converted to rubble. Clean break, no hang-ups. The shift engineer makes a note in the progress log. Advance 7 feet 2 inches. Overbreak minimal. Casualties 0. Tomorrow they'll do it again, and the day after that, and the day after that, until the tunnel is finished or the powdermonkey is dead.
The Central Pacific Railroad kept meticulous records. Item 347. Powdermonkeys. Cost per annum. $3 per day, 6 days per week. $156 per month. $1,872 per year. Item 348. Casualty replacement cost. 2 weeks training, 1 week observation. $84 total. Item 349. Insurance premium per worker. $12 per month for a $5,000 death benefit. Non-negotiable. Lloyd's of London will not underwrite explosive work at any other rate. This is the invisible architecture, the financial system that made 19th century expansion possible. Not the railroads themselves, not the tunnels or the bridges or the canals, the spreadsheets, the actuarial tables, the capital structures that converted human mortality into investment risk. The financing model was elegant. Private capital funded construction through bond issuances backed by future toll revenues. The bonds were sold to European investors, primarily British and Dutch, who understood railroad economics but had no direct visibility into construction risks. What they saw were engineering reports projecting completion dates and revenue forecasts. What they didn't see were the weekly casualty reports. The insurance companies bridged that gap. Lloyd's of London wouldn't underwrite a tunnel project without detailed casualty projections based on explosive type, worker experience, and geological surveys. The premium rates encoded the actual risk. A project using liquid nitroglycerin paid 40% higher premiums than one using gelatin dynamite. A project with experienced powder monkeys paid 20% less than one with new hires. The math was elegant. Pay a man $3 a day or pay 6 men $84 each to replace him when he quits. The latter costs more. So they paid.
But they also calculated acceptable loss rates. The industry standard, 1 death per 10 feet of tunnel advance. That's the ratio that maximized profit while maintaining political viability. Go higher and you attract regulatory attention. Go lower and you're leaving money on the table. The Hoosac Tunnel was 25,031 feet long. The final death toll was 195. That's 1 death per 128 feet, well below the industry threshold. The investors considered it a success. The casualty ledgers tell you everything about how this system worked. March 12, 1868, James Talbot, powder monkey, age 34, premature detonation during loading, cause, fractured fuse integrity, result, fatal, replacement cost, $84. July 3, 1871, Patrick Dunn, powder monkey, age 29, caught in blast zone during retreat, cause, fuse burn rate variance exceeded safety margin, result, fatal, replacement cost, $84. November 18, 1874, Chen Wu, powder monkey, age 41, struck by rockfall triggered by blast overbreak, cause, misjudged charge weight in fractured strata, result, fatal, replacement cost, $84. The names change, the replacement cost doesn't. This isn't callousness. This is 19th century industrial capitalism operating exactly as designed. Human labor as fungible input, risk as a line item, progress as the only metric that mattered. And progress was extraordinary. Between 1850 and 1900, North American railroads grew from 9,000 miles to 250,000 miles. Europe added 190,000 miles. Asia added 60,000. Every mile required tunnels, cuts, and grades blasted through solid rock. The men who did that work understood what they were part of. They saw the casualty ledgers. They knew the replacement cost. They knew that the system would continue whether they survived or not. And they showed up anyway, because someone had to light the fuse. By 1920, the job was obsolete. Electric detonators replaced fuses. The magneto-electric blaster, a handheld generator producing 60 volts, could fire 30 charges from 1,000 feet away. Turn the crank, close the circuit, detonate. No fuse, no timing, no walking back through darkness with a lit match. The powder monkey became the blasting technician. Muscle memory gave way to technical certification. The casualty rate dropped from 1 death per 100 feet to statistically negligible by 1950. But the tunnels remained. The Hoosac still carries freight, the Montseny through the Alps, the Woodhead under the Pennines. Structures built between 1850 and 1900 with hammers and dynamite and human calculation. No computers, no remote monitoring, just memorized tables and a tolerance for risk that would be illegal today. The modern world sees tragedy, exploitative labor, systems that valued productivity over human life. That's incomplete. Those men weren't victims. They were professionals who understood the risks better than anyone. They made a choice. Show up, do the math, light the fuse, walk away. $3 a day for work that could kill you before lunch. They did it well enough to build the infrastructure that defined a century. There's a photograph from 1873, Hoosac Tunnel, East Portal. 4 powder monkeys in the front row holding tin satchels. Their faces are blurred, 19th century exposure times, but their posture is unmistakable. Shoulders back, eyes forward, the stance of men who know exactly what they're worth and what they're risking. That photograph is the only monument. The men left nothing else. No memoirs, few names, no statues. They were invisible infrastructure, essential, expendable, erased by the progress they enabled. But the work remains. Every mountain pass you drive through was created by someone who understood nitroglycerin chemistry better than most chemists. Every train tunnel was fractured by someone who could calculate fuse burn rates in their head while walking through darkness. Every railroad bridge crosses an approach grade cut by someone willing to stand at ground zero for $3 a day. They were the manual fail-safes of the Industrial Revolution, the human algorithms who converted geological impossibility into engineered reality. They don't need our pity. They need our recognition. The powder monkeys blew the modern world into existence. Then they walked away, and the world forgot they were ever there.